Time for our bi-weekly colloquium. Shomak could not be here because he's in the middle of some meeting, and so I'm going to take over. It's a fantastic privilege to welcome Professor Roy Martens for this colloquium today. And Professor Roy Martens is a friend who has visited IUCAA quite a bit in the past. He has many friends at IUCAA, including, as you just now heard, Professor Naresh Dadich. And he is at present an SKA chair at the University of Western Cape. He was also the founding director of the Institute for Cosmology and Gravitation. He, until recently, was the editor-in-chief of General Relativity and Gravitation. So I actually have met Roy a long time back because we both had a common collaborator, John Barrow, and we met long back in Sussex at some stage when he was there. He works on a great variety of things, all aspects of cosmology, dark energy, inflation, and extremely active, very knowledgeable, and it's a pleasure to get him to talk about cosmological surveys with the SKA. Roy, please take over.
Thank you, Kandu, for that exaggerated introduction. It's a great pleasure and a great honor to be virtually back, even though it's only virtually back in IUCAA. I wish it was physical, but maybe later in the year or next year, hopefully. So today I'd like to talk to you about something that I've been speaking about many times over the years, but it keeps getting updated. So those of you who've heard something similar, I promise there is something new here. Just got to click on the screen here. There we go. I'll start off just by making a general point about cosmological surveys, not just with the SKA, but in general, and the SKA is not as well known for its galaxy surveys as, for example, the Euclid Satellite Galaxy Survey and the surveys with LSST, or now known as the Rubin Observatory, as well as many others. But what's the important thing about these next generation galaxy surveys? Well, they're distinguished from the current surveys, which is represented in the state of the art by the BOSS survey that's just completed recently. They're distinguished by their larger sky area and their deeper redshift reach. And so as a consequence, these surveys will be covering much greater volumes of the universe. And basic statistics tells us that the greater the volume, the greater the number of galaxies, and therefore the more precise the measurements. So the key thing that these next generation surveys are going to deliver is increased precision on the dark cosmos. In other words, the measurement of the properties of dark energy and dark matter. And that's obviously key and one of the foundation stones of cosmology. But I'm not really going to talk about that, which in itself is a big topic and of highest importance. I will focus on the new things that these surveys will facilitate, things which current surveys are not really able to do with any kind of robustness. And they will, in this sense, they will be delivering new probes of the universe because of their ability to access larger scales than current and previous surveys. And if you look at the plot that I have on the right here of the power spectrum of galaxies, the equality scale, which marks the turnover in the power spectrum, is already a very large scale. Current surveys don't quite have any, well, they don't have any statistical measurements at that scale. These new surveys will go past the equality scale to what I'll call ultra-large scales. I've indicated here on the right the scales which we could call large scales associated with the baryon acoustic oscillation scale, and then down to nonlinear scales, which are very important for redshift space distortions. So what is the basic idea with galaxy surveys as a probe of the universe? Well, it's just a very simple idea. The more galaxies you have, in other words, the bigger the volume, and also the more sensitively you probe that volume, the greater the statistical power. I will only be talking about measuring the positions of galaxies, but one can also measure their shapes to increase the amount of information that can be extracted using weak lensing. That's something I won't talk about, even though the SKA will make a contribution there, but I won't have time to go into that. But by measuring shapes and counting numbers in huge volumes of the universe, we are able to, first of all, deliver what standard surveys already do, but much better. That's constrain the dark cosmos. And then a number of new things which I've listed as uncovering imprints from the primordial universe, which current surveys are not quite able to do, to probe the geometry of the universe, which again is very difficult with current surveys, but will be done by these new next generation surveys and the SKA in particular, and to test general relativity on ultra large scales, which clearly is not yet possible. So what will the radio surveys delivered by the SKA actually bring to cosmology? And I'm showing here the Cosmology Red Book for the SKA, which was written by the SKA Cosmology Science Working Group, which summarizes what is expected to be achieved with phase 1 of the SKA. But the bullet points that I have below actually highlight two of the key issues. Radio surveys will actually probe the largest volumes in the universe, larger than optical surveys for various reasons. They have disadvantages, but that's an advantage that they have. And the second point is actually just as important, and that is that if we have radio cosmological surveys and we combine them with the more standard optical and infrared surveys, we can suppress a lot of the systematics by using this combination. And we can also suppress cosmic variance by using the multi-tracer method, which I will come to later. But let me quickly say something about the planned SKA. It's the biggest ever radio telescope, and physically it's the biggest ever astronomy experiment. In phase 1, which should start science commissioning around about 2025, all of these dates are always subject to increase, no matter what the survey is, whether it's SKA or Euclid, as you know. But in phase 1, the two instruments, the mid-frequency and the low-frequency instrument, respectively in South Africa and in Australia, will have 200 dishes for the mid and about 130,000 dipole antennas for the low-frequency instrument. I will only talk about the mid-frequency instrument because the low-frequency instrument probes mainly the epoch of reionization, which I will not be discussing. Whereas the mid-frequency dish array, the dipole antennas look something like this middle picture here. The dish array is the mid-array, the more familiar vision of a radio telescope. That is located in South Africa, and 64 of those dishes have already been built and are operating and carrying out science in the form of the South African precursor telescope, Meerkat, which is, many people think, currently the world's best radio telescope for lots of science cases. In phase 2, which is not yet funded and is still far into the future, at least from 2030, this is envisaged as 10 times more powerful than SKA phase 1. But I won't be discussing that, it's very futuristic. In phase 2, the SKA will actually spread beyond South Africa into Africa, which is important for us in Africa. So quickly, just to see on the map of the world here, sorry, not a map of the two sites rather, there's Australia, the Australian site in the Western Desert and the South African site in the central semi-desert area of the Karoo. And on the right are actual photographs taken from the air, the desert and the semi-desert area, which are particularly radio quiet. So let's come back to the science. And looking at this cartoon where time flows from left to right and space is vertical, starting with the beginning of the universe followed by inflation, we have this basically the developments that are important from the point of view of radio astronomy. After we've had the initial plasma phase and the decoupling with the cosmic microwave background at last scattering, we have, after the formation of neutral hydrogen, a period called the Dark Ages when neutral hydrogen is clustering very gradually and giving birth to the first generation of stars. In principle, this epoch can be measured by radio telescopes, but basically they need to be on the dark side of the moon in order to detect the extremely faint signal against the foreground noise, the foreground contamination rather. So the SKA kicks in when soon after the first stars form that begin to reionize the neutral universe, ending the dark ages with the cosmic dawn. And this is where SKA low comes in to measure the extremely interesting astrophysics and cosmology of the epoch of reionization, which I won't go into. The later development, when the universe is fully reionized, the neutral hydrogen is not destroyed, but the remaining neutral hydrogen is almost entirely within galaxies, shielded from ionization by various astrophysical effects. And SKA mid, the mid-frequency telescope, is designed to detect the neutral hydrogen in those galaxies and also to detect galaxies by other means, which I will come to shortly. I will begin with this neutral hydrogen detection. How can we detect neutral hydrogen? Well, there's this remarkable spin flip transition in the hydrogen atom where an aligned electron and proton has a slightly higher energy than an anti-aligned state. It's extremely small energy difference. It corresponds to a 21 centimeter wavelength photon, very low energy. And the transition rate is extremely low. So it's a very, very weak signal, but there are an enormous amount of hydrogen atoms in the universe. Hydrogen is the most abundant of the baryonic components of the universe. So if we have a galaxy containing neutral hydrogen, and if we can detect that emission, as soon as we detect the galaxy, we have a very, very precise measure of its redshift. So unlike optical surveys, where you typically first image and then go back and do spectroscopy, in a 21 centimeter galaxy survey, detection is the same as spectroscopy. So there's no imaging and returning. You just detect the galaxy and you have the redshift immediately. And it's extremely accurate, more accurate than the optical spectroscopic surveys like Euclid. But there's a downside to it. It's extremely difficult to detect galaxies. This is the catch, because the signal is so weak. So because of that, it turns out that SKA in its first phase will not be a game changer if we confine our attention to the galaxy redshift surveys. So we estimate in the Cosmology Red Book that the optimal survey will be 5,000 square degrees, about the size of DES and smaller than BOSS, out to a redshift of at most about 0.5. So this is not clearly going to be a game changer in cosmology. And the reason for this restriction to a smaller sky area and a lower redshift is simply the fact that it's extremely hard to detect that 21 centimeter line at cosmological redshifts. So what we have is a kind of compensation, although it won't be leading the game in cosmological measurements. This galaxy survey will provide a very useful complement to optical surveys such as BOSS and the optical next generation surveys on Euclid and other next generation surveys. So for example, with the BAO, the measurement of the Hubble parameter over redshifts from 0 to 3, I'll show here in this graph. This again comes from the Red Book. The SKA1H1 galaxy survey gives us measurements errors which are below 10%, but are certainly not revolutionary. What I've also shown here is the SKA 21 centimeter intensity mapping surveys in red and in pink, which I will shortly discuss. And here you see Euclid. So Euclid is well ahead of the SKA in terms of a spectroscopic galaxy survey. But nevertheless, having the survey in the radio at low redshifts provides a very useful complement to optical surveys. And the other thing that we could look at, for example, is redshift space distortions, where the errors on the growth rate, F, from the SKA Galaxy Survey are better than current data, well, data in 2018, probably a little bit better than BOSS, I'm not sure. Certainly not leading the pack such as Euclid will be doing. But once again, the intensity mapping survey will do much better. So what is this intensity mapping survey? Well, if we didn't know about intensity mapping, or we didn't consider it as a possibility, we'd be a bit stuck now. We would have to conclude that the SKA with a standard galaxy survey is unable to compete with other next generation surveys in optical and infrared. So this would mean that we wouldn't be able to do transformational cosmology in phase 1. But in fact, there is a way out. The answer to this question is no. And the reason for that is that it's not actually essential to resolve individual galaxies for cosmology. So you can think of the following: if I cannot detect individual H1 emitting galaxies, what I can do is integrate the 21 centimeter emission in each pixel. And what I'd be doing is something very much like the CMB, but at any redshift that I choose in the range of the telescope. So it's like a three-dimensional version of the CMB with extremely accurate redshifts. So this will allow us rapidly to map huge volumes. And the SKA1 is planned to cover a redshift from 0.1 to 3, so that's very high redshift reach, including the low redshifts, which are important. And the sky area is proposed at 20,000 square degrees, double that of BOSS. There is, of course, a catch, just like with the CMB, but even worse for 21 centimeter because it's lower frequency. The signal is contaminated heavily by foreground contamination. But it took a decade, or it took a few decades for the science of CMB foreground cleaning to develop to the state it is today with Planck. And 21 centimeter foreground cleaning is building on that experience, and I believe that within a decade or so, it will be at a very high level of technological precision too, so that we will be able to deal with this problem, but it is a huge problem that I have to mention. What about cosmology with the precursor survey MeerKAT? Well, of course, MeerKAT's, the possibility of a 21 centimeter galaxy survey on MeerKAT will be even more difficult, but intensity mapping is certainly quite feasible with MeerKAT. And there is a proposed survey which has not yet been accepted, but it's a proposal for a large area synoptic survey on MeerKAT as a pathfinder for an H1 intensity mapping survey on the SKA. And hopefully that will take place in the coming years and allow us to develop the experience and the pipelines for the major 20,000 square degree survey that is planned for the SKA. Right, so I'm going to leave now the specifics of instruments and surveys and come back to the first of the new science questions which I mentioned at the beginning of the talk. And this is probing the primordial universe using galaxy surveys. So if we take another look at the cartoon history of the universe, this time slightly differently with less detail, because what I want to highlight is the transition from inflation, where the seed perturbations for large-scale structure in the CMB are generated at a time less than about 10 to the minus 30 seconds, to the CMB at last scattering at about 400,000 years, to the galaxies which we measure in surveys from 1 gigayear onwards, roughly, up to today. So the basic idea is we're trying to think of signals generated in inflation which can be detected specifically in galaxy surveys. This is familiar from the CMB, especially in the form of primordial non-Gaussianity. So we know that quantum fluctuations are generated in the models of inflation that have been developed. For very simple inflation models, such as single field, slow roll, standard inflation, these fluctuations are effectively Gaussian. But for multi-field and other more complicated simple field models, they are non-Gaussian. And primordial non-Gaussianity is therefore potentially a powerful probe of inflationary models. The primordial non-Gaussian parameter FNL, where NL stands for nonlinear historically, if that parameter is less than about 1, if it's measured to be less than about 1, this will rule out many multi-field models of inflation. So in particular, the value of 1 is a good target to aim for. And if we can go below that, we'll be able to rule out more models of inflation. Quantum fluctuations, as I mentioned, seed the growth of large-scale structure. And primordial non-Gaussianity leaves a trace in that large-scale structure. However, there is a catch to this. The catch is that large-scale structure, unlike the CMB, develops through non-linearly through the growth of perturbations due to gravitational collapse. The CMB is much more linear, and it's frozen, if you like, at a redshift of 1,000, so it doesn't continue growing up until redshift 0 like large-scale structure. So unlike the CMB, in large-scale structure surveys, the non-Gaussian signal is completely wiped out on small scales. It's completely dominated by nonlinear non-Gaussianity. However, on ultra-large scales, this nonlinear growth of structure is no longer occurring. The growth is largely linear. And so the signal remains slightly contaminated, but not enough to destroy it on ultra-large scales. And that's the catch, that you can only detect this essentially if you're able to probe ultra-large scales or to get around the problem in some other clever way. So going back to our cartoon of the history of the universe, the idea is that the FNL is generated at inflation, depending on the nature of inflation, which we don't know, of course, which we'd like to constrain. It can be measured by looking at the CMB, and that's already been done, as I'll shortly show you what the answers are, or some of them. And then it also exists as a signal in galaxy surveys, where it's much harder to measure, but in next generation surveys, as I'll show, we can make real progress. So the state of the art in measuring this FNL parameter is represented by the Planck 2018 results. And FNL is measured to be minus 0.9, that's just the best fit value, plus or minus 5.1. So in other words, the 1 sigma error of the state of the art measurements today is 5.1. That's significantly above the target of 1 that we'd like to reach in order to rule out a large class of inflationary models. But nevertheless, it's much, much better than anything you can get from current galaxy surveys, which cannot compete really with Planck. However, future CMB experiments are not really going to do any better. Future CMB experiments will mainly cover the small scales that Planck has not done so well on, look at nonlinearities, although they will also look at large scales for B modes and for polarization, but that's not really going to contribute much to reduce this error on FNL. It's only galaxy surveys with their 3-dimensional information as opposed to the CMB's 2-dimensional information that have the capacity to bring this error down dramatically in the future. So how will that actually work? Well, it's a basic fact that non-Gaussianity in the linear power spectrum of dark matter is 0. In dark matter, the primordial non-Gaussian signal is non-zero only from the bispectrum onwards, bispectrum, trispectrum, and higher dimensional correlators. But this is not true for galaxy surveys due to a subtle effect of essentially a bispectrum effect in the squeeze state on the galaxy power spectrum via the bias of galaxies. So I can't go into this in technical detail, but if you start with a standard model for bias in the co-moving frame of galaxies and dark matter, the bias on large enough scales is scale independent. So I denote that by a bias function, which is a function only of redshift. Provided you do this in the co-moving gauge, this is a physically meaningful statement. It won't change when you the physical content does not depend on the gauge once you define it in the co-moving frame. But this only holds in a Gaussian universe. You can show that in a non-Gaussian universe, this scale-independent bias is corrected by a scale-dependent correction, which is proportional to FNL, but scaled by the Hubble parameter squared over k squared, where k is the wave number. And this formula holds provided k is less than k equality, so only on ultra-large scales. On smaller scales, the form of delta B is heavily suppressed and it's effectively negligible. So what this means is that the galaxy power spectrum, unlike the dark matter power spectrum, does indeed carry a fossil signal, but on ultra-large scales of primordial non-Gaussianity. The dark matter power spectrum does not carry this signal. But of course, what we measure is the galaxy power spectrum, so this is to our advantage. But because the signal is only non-negligible on ultra-large scales, we do need ultra-large volume to access this information if we want to constrain FNL. So what I show here is these forecasts are a few years out of date and the specifications of the surveys have changed slightly, so there will be some changes here, but this gives you the general idea. If we consider the three surveys that I've highlighted, apart from SKA, that being Euclid and LSST, this plot is showing from 2015 a forecast for the error on FNL with the floor that we're aiming at of 1 right at the bottom here. The error on FNL as you increase the maximum redshift, in other words, as the volume increases. So in red, we have LSST, which gives us in its full form just about the best constraints, followed by SKA intensity mapping, and then followed by Euclid. You can see that although they do very well, LSST and SK1, they do beat Planck, but not by that much, and they don't actually allow us to break through this threshold of 1. So this is a reflection of the fact that no matter how large and effective your survey is, even if you ignore the noise, as you see in the purple and blue dashed lines, you're still not able to get to this threshold of 1. And that's because you just do not have enough scales which are ultra large to be able to measure to get the statistical power on FNL. So it seems that perhaps when I said galaxy surveys will be able to break through this limit, that I was wrong. But in fact, there's a way around this, because the natural question is, can we combine these different results in order to improve on the answer, on the error, on the precision? How do we push this error below 1? Well, there's a very interesting thing called the multi-tracer method, where we combine two surveys which are looking at different traces of the dark matter. And in the case of intensity mapping and say Euclid, or intensity mapping and LSST, those are very different traces, different dark matter halos that we're looking at. If we have two different maps of the same underlying volume of the universe, this underlying volume is based on the dark matter field, which is stochastic. Each of these traces has a bias. Tracer 1 has a bias B1, tracer 2 has a bias B2. Roughly speaking, if we divide the two maps from the different traces, we knock out the stochastic dark matter field. So we remove the cosmic variance, and we have a cosmic variance-free measure of the ratio of the biases. Of course, we also have to take the noise into account, and there are all sorts of other complications, but the suppression of cosmic variance is real by this method, and it actually does work. So if we apply this multi-tracer method, which basically consists in taking cross-correlations and autocorrelations and combining them in the statistically optimal way, we find the following results. If we combine in SKA1 intensity mapping survey with Euclid, we can get down to 1.1. Not quite there, but a remarkable improvement on what we have currently. But even better, if we use LSST, which has a significantly larger volume than Euclid, we can get down to 0.67. We can break through that barrier. And in principle, we would be able to rule out a large number of inflationary models as a result. So that was my first example, which I indicated at the beginning of this talk about new probes of the universe being able to take us into new knowledge of the cosmos. This is the main result, probably, of the talk, the first one on probing the primordial universe. But before I move on to the next one, let me just pose the question, is there anything we can do with the multitracer before next generation surveys arrive? And there is one obvious example to consider, and that is a MeerKAT intensity mapping survey combined with a DES photometric survey. DES is like LSST, it's photometric, and it has a high number of galaxies, which is good for FNL. And MeerKAT, of course, is a precursor for SKA. So this is like a precursor for SKA cross LSST. On the plot here, I've shown the error on FNL that one can get from DES alone. It's about 12. It's actually very good. Maybe our forecast was a little bit optimistic, but it's still, this would be the state of the art. It would be better than any other survey, single survey currently. But if we consider MeerKAT cross DES, then we get these two dashed curves here, the blue one being the low redshift band of SKA intensity mapping, and the red one being the high redshift band. And we see that as the sky area is increased, the error goes down. 5 is about the threshold here, and MeerKAT cross DES could actually beat Planck before SKA and LSST could deliver results. So that's a hopeful possibility, and we are hoping, as part of the MeerKAT collaboration, we're hoping we'll be able to actually perform an experiment like this in the coming years. Right, my second and possibly final, depending on time, but possibly this is the final one. My second new probe of the universe is on testing the geometry of the universe using galaxy surveys. And this is one aspect of testing the geometry. There are other tests that one could think of, but this is the one I'm highlighting, which is not currently practical. So it starts with the common knowledge that we are moving relative to the CMB rest frame, which induces a dipole that is about 2 orders of magnitude higher than the temperature, the other temperature anisotropies in the CMB. And that's a simple special relativistic transformation of the CMB temperature, showing that there's a factor of 1 plus the direction of observation dotted with the relative velocity. So that in the direction of the movement, the CMB appears hotter, and in the opposite direction, it appears cooler with modulation in between. And this relative velocity is about 10 to the minus 3 times the speed of light. That is the actual, our relative velocity as deduced from Planck and WMAP previously, and even WMAP's predecessor, COBE. This is well known. What about galaxy surveys? Where do they come in? Well, the Copernican principle tells us that the universe should be isotropic about us on average, and that means that the galaxy rest frame should coincide with the CMB rest frame. In other words, the dipole velocity extracted from galaxy surveys should agree with the dipole velocity V0 above, which is extracted from the CMB. If this is not the case, then in some sense, there's a violation of isotropy, statistical isotropy. So this is actually a critical test in principle of the standard geometry of cosmology. And it was first proposed by Ellison Baldwin in 1984. The kinematic dipole in large-scale structure is similar to the temperature dipole in the CMB, in the sense that number counts of galaxies will be higher in the forward direction and lower behind us. If we were thinking of 21 centimeter intensity, the brightness temperature would be higher in front and lower behind. But I'm not going to be discussing the 21 centimeter survey, I'm going to be discussing a different radio survey. Come to that shortly. How does this work? Well, just quickly, I just wanted to identify, because it's interesting perhaps, there's a Doppler effect on the redshift that affects obviously galaxy number counts, so that the observed redshift by the moving observer corresponds to the rest frame of redshift by a factor 1 minus n dot v naught. And there's an aberration which affects also the CMB, that's just the change in the solid angle for the moving observer, 1 minus 2 n dot v naught. Since the number of galaxies in the rest frame and in the moving frame is the same, you can deduce from these two equations that the number counts per redshift per solid angle should be modified by a factor 1 plus 3 times n dot v naught, unlike the single 1 in the CMB. But if we also take into account the flux of radio galaxies, which I'll mention, which I'll come back to, this 3 gets converted to a slightly larger factor, roughly 3.75, depending on the flux properties of radio galaxies. So there are 2 current surveys with very large sky area. Clearly, we need a very large sky area to pick out a dipolar signature. This is on the very largest scale, so it's no good having BOSS or other surveys that have a smaller survey area. We need a survey area of at least 20,000 square degrees, probably, to pick up the signal. Well, we do have 2 such surveys. First of all, the older survey called NVSS, which is on the JVLA, the telescope based in America. And then the more recent survey, the TGSS survey on India's GMRT telescope. And these 2 maps show the dipole that can be extracted from those 2 radio continuum surveys. So these are surveys which have already been conducted, and they are not 21 centimeter surveys that I've been talking about. They introduce you, unless you already know about them, to a new kind of radio survey called the radio continuum survey. These surveys do not face the problems of foregrounds that the 21 centimeter intensity faces, and they do not face the problem of requiring huge sensitivity to detect galaxies that the 21 centimeter galaxy surveys face. The catch is that they don't give us redshifts. And the reason is that they are detecting radio galaxies like AGN and star-bursting galaxies and other high-energy galaxies, mainly through synchrotron radiation, but also through free emission. So they're detecting galaxies by their huge energy outflows that generate associated radio waves from electrons and other such electromagnetic processes. But these detections do not come with a redshift. Now, when we're trying to measure the dipole of the large-scale structure, that is not a problem. We can project all of these measurements onto the sky, and we do not really essentially need the redshifts of these galaxies. I'll come back to that point though shortly. So that was a little diversion just to explain to you what radio continuum surveys are very briefly. I apologize. So why haven't we already done these tests? Well, these tests have been done, but it turns out that the dipole measured by both of these surveys, especially the TGSS survey, is much larger than expected, although the direction seems to be consistent with the CMB direction, although with very large errors. And essentially, a conservative view would be that the data is just too noisy for a reliable dipole measurement. Essentially, the dipole signal is of the same magnitude, roughly, as the noise. And so it's extremely difficult to make any kind of robust statement about testing the geometry of the universe using current surveys. The Australian precursor survey on the telescope, the survey EMU on the telescope ASCAP. ASCAP is the Australian mid-frequency precursor. It's something like Meerkat, but it's different in many ways, which I can't go into. It is currently conducting the Evolutionary Map of the Universe survey, which is a radio continuum survey of 30,000 square degrees. And this survey is forecast to be able to deliver a robust measurement, which would be before the SKA does so. So that would be very useful if we can do that even before the SKA, but there's still a couple of years yet before we're confident that EMU has overcome all the problems that it's currently facing and that we'll be able to make such a measurement. It's still in the early pilot survey phase, EMU, but very exciting possibility. But if we turn to the SKA, the SKA is forecast to have exactly the features that one needs to make a robust test, which are very large sky coverage, because we want to measure the dipole, a high number density, because of the statistical power that we need to overcome the noise, and a high redshift reach, because we have to get beyond the very low redshifts where nonlinear effects contaminate the dipole to the point where we can't actually measure it. So what happens with SKA, the SKA phase 1 radio continuum survey, simulations show us the following plot of numbers, number counts as against redshift, and you can see two things here. First of all, you can see that the number counts are very high. So we're talking about hundreds of millions of galaxies in total. And secondly, you can see that the redshift is going all the way out to almost 6. Even though the numbers are going down, this is still a substantial amount of contribution to a signal for something like the dipole. So how do I deal with the low redshift nonlinear problem? Because effectively one has to remove those galaxies which are contaminating the signal. And in order to do that, you need the redshifts of the low redshift part of a radio continuum survey. And the SKA intensity mapping survey, together with optical surveys, are precisely the methods that we would use through cross-matching to actually pick out the redshifts of the low redshift part of an SKA survey and remove them so as to enhance the measurement of the cosmological signal. So doing that in simulations, we arrive at these maps which I'm showing you for the measurements of the dipole, which are shown in red, and the ones in blue are when we've removed the low redshift contamination, and the red dot is the direction of the CMB dipole. These simulations show us that, well, they predict. These are predictions, of course. These simulations predict that SKA radio continuum survey could measure the dipole with about 5 to 10% error, depending on the level of sensitivity that is achieved. And 5 to 10% is good enough to give us a robust test of the cosmological principle. So I think I should probably stop there. I do have a third topic, which I could go through in rather quickly, but if there are no questions, then I'll do that. But otherwise, let me stop and take any questions or comments that people might have.
At present, I don't see any questions, Zoom hand raised. Maybe Roy, you could continue.
Okay, so thanks, audience. For my third and final new probe, something a little bit different. And this is to do with the point which I highlighted in the beginning of testing general relativity on ultra-large scales. So this is a particular test of general relativity on ultra-large scales, which has recently been proposed. And it works as follows. If we consider the leading order relativistic correction to number counts of galaxies or to 21 centimeter intensity maps, it is a Doppler correction. And it turns out that in the power spectrum of galaxies, this Doppler correction is very hard to measure. It's like trying to get FNL equals 1 because it scales like 1 over k squared. But in the bispectrum, the same signal, i.e. the Doppler effect, now scales as 1 over k, not 1 over k squared. And so it becomes more accessible to go after the signal via the bispectrum rather than the power spectrum. So what I've shown here obviously this is just a formula for the multipoles of the bispectrum. You integrate the bispectrum over the angles of orientation of the triangles in Fourier space with spherical harmonics. And when you do this, you can identify the most measurable moments, the monopole and the quadrupole. And what happens is the following, that the monopole and the quadrupole, the standard multipoles of current bispectrum analyses, so-called Newtonian analysis, are real, and they're given by the standard Newtonian analysis. There is no Doppler type contribution to the monopole and the quadrupole. So you might think, well, that means we can't measure your Doppler type contribution. But in fact, the Doppler type contribution contributes a dipole. This dipole is purely imaginary, and it is exactly zero if we neglect the leading relativistic correction. Now, we can only neglect that correction if we abandon general relativity. It is there, the correction is there. It's not an option, except if you don't believe in general relativity. So it's a potential smoking gun of general relativity. And because it's scaling like 1 over k, we know that just like FNL, it's going to have to require ultra large scale surveys in order to detect if it's at all detectable. So the question then is it detectable in principle by next generation surveys? So I'll show you here an example from an SKA1 intensity mapping survey at Redshift 1. B00 is the monopole. I'm not showing the quadrupole here. This is the dominant part of the bispectrum. And here are the two components of the dipole. And you can see that for small wave numbers on large scales, that the dipole becomes non-negligible. So it looks like there's a possibility that especially in squeezed shapes, which is what we're getting over on these very large scales here, in the squeezed bispectrum, it looks that it might be possible marginally to detect this. Well, if we go and do the signal to noise analysis for this, with a 21 centimeter survey, intensity mapping survey on the SKA, what do we find? Well, first of all, I'll just remind you that what I actually said earlier, let me say it again. The GR Doppler correction in the auto power spectrum is not detectable because it, as I said, it scales like h squared over k squared times the matter power spectrum. And that's just too much suppression on large scales, just like FNL. But in the auto bispectrum, this dipole that I'm mentioning, this pure imaginary dipole, scales like the power spectrum squared suppressed by h over k. So that's why there's more chance of detecting it. That's another way of saying what I've said already. The reason that the bispectrum is better than the power spectrum is because, unlike the power spectrum, the bispectrum couples long relativistic modes with short wavelength Newtonian modes. The power spectrum can't do that at linear level. So if we do the signal to noise analysis, first of all per redshift and then the cumulative on the right, we find that, forgetting about Meerkat, just look at the red and the blue curves and then think of adding them together, we find that we can get a signal to noise of about 5 or less. So it's marginally detectable. It's not wonderful, but it would be detectable if these forecasts have sufficiently taken into account all the systematics, which of course is always a big if. I should just point out that in this particular sense, Euclid outperforms the SKA because the signal to noise that it delivers is of order 10 by contrast. It's well above 10 by the same prediction formalism. So that concludes my third probe of the new probe of the universe, which is facilitated by the SKA in combination with other next generation surveys. And that is where I'll stop. And while people are thinking of questions, I could just put up some slides about the SKA site in the Karoo. I'll do this silently while people are thinking of corrections.
Thank you very much, Roy, for this fascinating talk about the SKA. People can now raise their Zoom hands and ask Roy whatever questions that they want to ask. Sanjit, can you unmute and ask your question?
Yeah, can you hear me?
Yes.
My question is about the dipole measurement. So, see, there are these two surveys you said that which already measured the dipoles, and the measured value is much larger. So, is it believed to be due to a systematic effect, like, for example, selection bias? If that is the case, then how SK is going to address that? Even though there is a large number of galaxies, and the error is going to come to 5 to 10%. If there is a systematic effect, it is going to stay, right? I mean, just.
Well, I can't claim to be aware of all the systematic effects, but one obvious reason that the dipole is too large in the existing surveys is what I mentioned, that the dipole signal is the same, well, the noise is as large as the dipole signal. So trying to extract something which is basically barely above the noise is not going to work, regardless of systematics. Systematics are an additional issue. But one thing that the SKA will do, and EMU as well, is that the noise will be dramatically reduced if these surveys are successful, which they eventually should be. And so the signal should be well above the noise. Now, you might still face systematic issues, but every survey, every measurement faces systematics. And I'm kind of just assuming that those things are taken into account. Whether it's radio or optical, every survey faces systematics. The systematics in the Continuum survey are different from in the intensity mapping. Intensity mapping's worst systematic, if you call it that, is foreground removal. You don't have that problem with the radio continuum. But I can't answer your question about the details of such systematics. I'm just confident that they can be dealt with. You know, there are far more complex measurements planned for these surveys, which people are confident they can make. You know, constraints on dark energy with a radio continuum, weak lensing with a radio continuum. So a lot of people are looking into systematics, not trying to measure the kinematic dipole, but for other science. But the systematics will be likely to also affect the dipole. So I'm sort of confident that the systematics can be addressed.
Great. Surut, can you go ahead with your question?
Yeah, thanks, Kundu. Thanks, Roy, for this wonderful talk. I wanted to ask you about these non-Gaussianity constraints that you showed, which
Yes.
are possible with SK intensity mapping experiments. You had shown two different curves, basically, for the possibilities of how you can constrain FNL, for example, using SK. So are there... yeah, here, right? So you said there's a noiseless curve and a one with noise. So is this systematic noise, statistical noise? And if it is systematic noise, do you know where are the known unknowns and the unknown unknowns, right? So is this actually accounting for systematics that you know of that can be taken care of? Or, yeah, so I wanted to know this budget of systematic noise.
Sure. No, this is just shot noise in the case of Euclid and LSST, and thermal noise in the case of SKA.
I see.
So for an intensity mapping survey, the shot noise is negligible. The thermal noise is significant. So that's the thermal noise.
Okay, so there's no systematic foreground removal issues which are dealt with here. So
I think when you're forecasting for future surveys, until you get to the point where you're starting to construct a pipeline for a survey that's about to start,
right,
you're likely not to deal with the systematic. So these are the 2015 kind of simulation and Fisher type forecasting where you admit that the systematics will have to be dealt with. Right. When you actually start creating pipelines like they're doing for Euclid now and LSST, and they're starting also with SKA. It's a little bit behind.
Yeah.
Then you have to construct pipelines which actually start feeding in the systematics into your forecast. So they're
Right.
not taking.
But is there like an expectation of a 1 over k square kind of systematic?
So the systematic, the issues which are known for galaxy surveys are stellar contamination, for example. That gives a large scale systematic. And the obvious one for SK intensity mapping is foreground removal. Because the foregrounds are almost smooth in frequency, when you remove them, you lose power on the largest scales. So that is the big issue for intensity mapping, and the big issue for galaxy surveys is stellar contamination. So those will further worsen these constraints. But of course, the better you can deal with these systematics, the less the damage. I think the point of the multi-tracer is that you partially can get rid of those, or you can damp down those systematics. Because when you cross-correlate, say, a galaxy and an intensity map, you get no foreground and no stellar contamination, because the cross-correlation doesn't pick them up. Of course, they come back at you when you factor in the autocorrelation, so you can't get rid of them, but you can mitigate them. You can help to mitigate them with the multi-tracer.
Shubir, you had a question, but you couldn't raise your hand.
Yes. Thanks, Roy, for a very nice talk. Concerning this dipole in the radio sources, I share your concerns about the signal to noise and so on. But of course, there is a independent way to do the same thing, which is to look at high redshift sources whose redshifts have been actually measured, as opposed to simply guessed from the luminosity function, as you're doing for the radio sources. And that is quasars. And I don't know if you're aware that we have recently used a catalog of nearly 1.4 million quasars gathered with the WISE satellite. This is the CatWISE catalog. And we see this dipole signal at 4.9 sigma, significantly above the kind of detections that have been made earlier in the radio surveys that you mentioned. So I think it's getting pretty compelling. And actually, in that context, I wanted to ask you, obviously, we hope to have confirmation of this with SKA, but you didn't actually say how you would establish the redshifts and thereby rule out the possibility that it's a local clustering dipole. And obviously, you're aware of the issues involved. Are you not planning to coordinate with a redshift survey to at least sample part of the sky to get a representative redshift distribution?
Thanks for those comments, Sabir. On your second point first, yes, people are planning, definitely. There's quite a lot of work being done on cross-matching radio and optical surveys in order to, on the one hand, get redshifts for a radio continuum, and on the other hand, to improve the photometry for optical surveys. So there are two different branches of such efforts. The one that's relevant for the dipole, as you point out, is to get the redshifts for continuum survey, radio continuum survey. And I think I'm not familiar with the latest work on this, but I think if you think of relatively low redshifts where we've got quite good coverage by optical surveys and where we will soon, well, on a next generation timescale, we will also have intensity mapping measurements, hopefully, which have very good redshifts. We could be quite hopeful that we would be able to identify the redshifts of a significant fraction of those radio continuum sources in order to remove them. But I do admit, and I'm sorry that I forgot about this, I did see your quasar paper and I forgot to factor it in here. I suppose because it didn't really fit into the story of mine about next generation surveys, because you actually remarkably managed to use a measurement of current surveys. And I do admit it's a very, very interesting and exciting development. I'm just not familiar enough with it to have put it into my talk either, I suppose.
Oh, that's not a problem. My specific question was, as you say, there is a kind of a choice between large angle, well, large coverage, sky coverage, but shallow surveys, and a few deep surveys where you have spectroscopic redshifts, as from SDSS, EBOS, and so on. So the question is, for the large full sky surveys that you are mentioning in the optical, those would be photometric redshifts. So my question was specifically, are they, has anyone done a study of, will those be accurate enough for the job that we need to do? Or should we, as we did with the quasar work, rely upon only sampling a small fraction of the quasars? We could only get redshifts for about 10,000 of them. From a little strip that had been also looked at by EBOS. But, you know, as long as one can argue that that was a randomly chosen strip, you could take it to be a kind of a representative of the whole population. But
So
for the radio sources, you could do better, perhaps.
If I'm allowed to use the method that you used, then
Yes.
I would say we could use much smaller area optical surveys and an intensity mapping survey
Yes, yes.
to do the same thing.
Excellent.
So although you, as you say, optical wide surveys are photometric, but intensity wide survey is spectroscopic.
Mm-hmm.
But yeah, we could use, say, the 5,000 square degrees or the 10,000 square degrees of an optical survey and make the same argument that you made.
Yes, yes.
I'm a bit nervous of that argument, but you're the expert. So if you do...
Why are you nervous? That's what I'm trying to get at. Why, do you have any concerns that one should think about?
Yeah, I need, you know, on my list of exciting papers that I was supposed to read, which just gets longer by the day, unfortunately. Your paper's there, and I haven't yet got into it.
Thanks. I'll send you an autographed copy.
Okay, with that, Shubir, thanks.
Yeah.
Sriram, you had a question.
Hi, Roy. My question is, will you be able to measure FNL in arbitrary configurations, triangular configurations, or only in the squeeze limit?
Very good question. So if we use the bispectrum, then we can go beyond the measurement of the local type that I've actually been discussing. So this FNL that I'm talking about is the local primordial non-Gaussianity. Peaks and squeezed shape.
The reason I'm sorry, go ahead.
The equilateral shape is effectively unmeasurable in the power spectrum because it's degenerate with Gaussian bias. And the flattened shape has a very weak signal. I'm not sure if anyone's, I know of work that's looked at that, but the constraints are quite weak. Planck itself has pretty weak constraints on non-squeezed cases. But yes, if you use the bispectrum, then you can, in combination with the power spectrum, which people are starting to do, then it's conceivable that you can extend this to other shapes.
The reason I'm asking is that there have been arguments over the last couple of years that the squeeze limit of the bispectrum is not measurable. It's not an observable.
I think this is a slightly different point. What is not observable is any non-Gaussianity from simple single field slow roll inflation. So the debate in the community started off, I think, with a original result showing that the FNL from standard slow roll inflation was proportional to n-1, where n is the slope of the primordial power spectrum. But it was subsequently shown that that's a purely projection or observational effect. And when you go from global coordinates to local coordinates, you find that single field slow roll inflation has an FNL of 0. It's not measurable. But the bispectrum is measurable if, FNL is measurable in the power spectrum and the bispectrum, provided there is a primordial inflation model which generates it.
The point is, many of the single field, and I am not able to comment about two field models, generate FNL which satisfies that relation you mentioned, which means it is unobservable.
Well, the ones that do that are all either like the standard, they're the standard one, or they're like the standard one. So for example, in ultra slow field inflation, because that has to end in a standard phase, that transition actually leaves an imprint, which is measurable. But it's also true that in every two-field model, like the curvaton is the best known one, every two-field model will generate non-zero FNL, definitely measurable in principle. And the string theorists would be very upset if I didn't acknowledge that there is likely to have been lots of fields in the early universe. So I think you could really phrase it, if you like, as a kind of a rough test of multi-field inflation. I think there are also single-field models like DBI inflation, Dirac-Born-Infeld inflation, which also leave a measurable in principle non-Gaussian signal.
Thank you.
Okay, Asim, can you please go ahead?
Hi, Roy. Nice to see you again.
You too.
So I had a general question about these ultra-large scale GR effects that I know you've been modeling quite a bit over the last few years. So have people looked at trying to develop some kind of parameterized post-Newtonian framework now on large scales to look for departures from GR? Is there enough information at these scales that you can ask such questions? Because I know that people want to do this with RSD, but at large scales, you're directly probing GR in some sense. So
yes, there is some work on a PPN type formalism, although the main intention there is to try to bridge the gap between linear theory on very large scales and nonlinear perturbations on small scales. And the intermediate regime is where this PPN type formalism has been applied, either in GR or in modified gravity theories. So I think that on ultra large scales, the standard law would be that you're fine with a perturbative expansion. You can go to second order and you've covered all your bases. The big caveat, and you know this much better than me because you're an expert on it, is modeling galaxy bias or halo bias in general, where it turns out that short scale effects have an imprint on large scales. So if you can control that, I think that's the real issue rather than a PPN type formalism. Because I think, aside from bias, the problem of halo bias, a perturbative analysis is almost certainly very accurate. It's like the CMB. These signals are weak enough that they should be entirely perturbative. But then they get mixed up in measurement with the galaxy bias. So there you have to bring in nonlinear effects, which I don't think PPN type approaches would help us with. But like this effective white noise. You've got this effective white noise on ultra large scales from bias terms. People usually just absorb it into the shot noise, or maybe absorb it into the thermal noise of intensity mapping, which is probably fine. But that might be an issue for what's going on ultra large scale measurements. So, yeah.
Okay, thanks.
Shantanu, can you?
So maybe I want to ask on something you touched at the very beginning of your talk. So I guess, is there one sort of acid test which SK can do of LCDM versus like other alternatives such as self-interacting dark matter, fuzzy dark matter, superfluid dark matter, which Euclid or LSST cannot do?
I think the answer is probably yes, but I'm not personally familiar with such a test. I'm aware of people who test dark matter models and who are quite excited by the SKA because these dark matter models will generate electromagnetic signals that in some kind of combination with baryonic matter often ends up generating a radio signal. So I would say the answer is yes, that particular kind, if you look at the whole range of dark matter models, there's certainly some that are going to have radio signatures that SKA potentially could detect. And I am aware of papers like that, but it's just something I'm not technically familiar with. That there may be other things too. You mentioned that, and I think that's probably the main one. You know, for example, there's a radio Zeldovich type effect from radio halos around radio galaxy. It's another thing which I'm not technically familiar with, but which people have been putting forward as something that the SKA might be able to detect, this radio Zeldovich effect. And perhaps the most important one, now that I look at Kandu, or suddenly I remember, I forgot it, is of course magnetic Faraday rotation measurement in the radio are going to give us a lot of information about magnetic fields in galaxies, which optical surveys won't be able to do.
Okay, Ajay Sharma.
Hello.
Yes, can you go ahead?
Hello, Roy. Actually, my question, basic question, how the primordial non-Gaussianity can transfer into the galaxy survey?
So basically, they're imprinted originally in the perturbations. So the perturbations of number counts of galaxies already contain within them the signal from the seed during inflation. So inflation generates the perturbations. During inflation, there's not radiation, so there's no CMB yet. There's certainly no galaxies. The curvature and the density of dark matter and the density of radiation all carry an imprint, curvature perturbation, they all carry an imprint of this primordial non-Gaussianity from the inflationary mechanism. So at each epoch where the transition from inflation to the plasma, from the plasma to the last scattering, to the CMB's last scattering surface, from there to the dark ages and so on, at each transition, this imprint is not destroyed. It's still there. But I think the point that I was making on this slide that I'll show here is that on BAO and smaller scales, and the traditional scales, the scales where the signal of galaxy surveys is strongest and the precision is highest, on these scales, that signal is completely wiped out. It's much smaller than the non-Gaussianity that is developed by gravitational collapse, gravitational evolution. So it is always there because it was imprinted and it cannot be destroyed, but it can be contaminated to the point that it's unmeasurable, I think is a quick answer.
Oh, thank you.
Thank you. I don't see any other hands raised, and we have had quite a lot of questions. So thank you very much, Roy, for this wonderful talk, presentation, and very clear. I hope you can have further lunch later. We are not able to clap our hands, but I can certainly clap for everybody. Thanks a lot, Roy.
Thank you very much.